Thanks, Bala. Good to see everyone this Friday afternoon, and we're very honoured to have Professor Sisi Zlatanova present to us today in our City Futures Research Seminar. So before we get started, I'd like to show my respects and acknowledge the Bejigal people, who are the traditional custodians of the land on which I'm on, and welcome to this virtual seminar. So I've known Sisi, it must be close to a decade, I think. I think we met in Beijing in the International Society of Photogrammetry Remote Sensing ISPRS Congress. So Sisi is president of one of the technical commissions for ISPRS. She holds many appointments. I'd spend the whole presentation talking about Sisi's appointments and positions on very esteemed international bodies and national bodies. She is, I'll just point out a couple of other points with Sisi's work. She's contributed and made huge impacts on the Open Geospatial Consortium work on standards. She's been looking at a number of areas in looking at data structures, data models, geospatial models. She's going to talk around 3D models of voxels today. And Sisi is one of our sharp professors within the School of Built Environment. She leads many projects, including a digital twin project in Western Sydney. And I'll hand over. Oh, and she is, of course, the director and head of the GRID group at UNSW. So thanks, Sisi. We look forward to your presentation.
Thank you, Chris. And it was very kind of you to say so many words about me. And thank you for inviting me to this series of seminars. I followed several of them, and they're very interesting. Today I was wondering exactly what to show to you and what to talk about. Our interest within our group is exactly on 3D modeling, and everything what we are doing is related to 3D, but specifically what we start liking very much in the last years is this modeling with voxels. So I decided to discuss with you what can be done with voxels. In all my presentations, somehow I say something about voxels, but this is going to be a lecture dedicated to voxels. So what is it, what are the challenges, and what are the opportunities? And before we start with the voxels, so everybody knows what is we are trying to do. Actually, we are trying to model the urban environments to be able to provide some kind of virtual models or kind of digital models to different kind of applications. And those different kind of applications can be urban planning, can be something related to disaster management, to smart city, all kind of different applications. And in a way, depending, of course, on the application, we can work in the two-dimensional domain, work with maps, but we also can go to the third dimension. And especially nowadays, when we start having more and more building information models, we are trying to provide more geometric information in 3D. And here comes really the very exciting part about voxels. In addition to the 2D vector maps, actually we have a lot of raster maps. And if we think in the same direction, going from 2D to 3D in the raster domain, we are getting something which is exactly related to the voxels. And therefore, I have this kind of very generic picture, and probably you have seen her in some of my presentations, that we are modeling the real world in two different types of representation, vector representation and raster representation. And when the raster representation becomes three-dimensional, we are talking about voxels. And the same issues that we have in general for the a vector domain, everything related to data models, data integration, management, data mining, analysis, sharing, visualization, and communication. This also relates to Voxel domain, and all these, let's say, issues that we have to solve in the vector domain, they also exist in the raster domain. But the raster domain is a little bit easy when we start talking about 3D analysis. And slowly, I hope I'll convince you that 3D analysis are, in a way, easier in the voxel domain. So let's start from the beginning. What are voxels? They're very similar to pixels, a regular distribution of information into the space. And usually voxels are associated with cubes, but they can be also tetrahedrons or other kind of shapes with regular facets. The good thing about voxels is that they're really discretized the whole environment, they're homogeneous, which leads also to a simple data structures. And because the whole space is subdivided into some kind of cells, then the operations become much more easy. And in a way, voxels are not new. They're used quite a lot in all kinds of different domains. Here you see some applications related to sea or water management, to human body management, geological substances, tree modeling. But more and more voxels are starting to be used also for objects and features above the ground, for modeling all kind of assets. And this is because of Minecraft, basically, because Minecraft, I guess many of you know what Minecraft is, but this is a game engine, and it started probably developing something like 15, 20 years ago. And it provides environment where with cubes you can model the real world, and you can model everything. And even nowadays there is a kind of initiative to build the whole Earth in 3D. So this is the website where you can register and you can do some modeling by yourself. I just checked before the presentation, and I realized that at this moment there are about above 200 members participating in this building the virtual world in Minecraft with cubes. And at that moment there are about 40,000 online building in different parts of the world. And everything can be built, not only houses and trains, but also formations, and you can dig in the ground and create plants and rocks and everything. So we also had this kind of inspiration to go to voxels from Minecraft. And this was back when I was in Netherlands. We are having experiments for public participation with kids. So we had several of these sessions with different type of school girls and boys, and they were given parts of cities, and they were asked to develop these parts the way they want to have it. And usually these were kids from the neighborhood where some areas supposed to be redeveloped. And here are some examples of what they are discussing about and trying to model by themselves. This was some kind of industrial area with storage place, and it was supposed to be redeveloped. So this is the area before. And here are some of the designs that kids made by themselves. You see, all of them were kind of very inventive, trying to make spaces for to play, or McDonald's to go to buy sandwiches, or some funny kind of places where they can run together. Okay, Minecraft in general is very nice, but when we go to real applications, there is, of course, quite a lot of disadvantages. This is a game, and you have to do everything manually. And there is a scripting language, and it allows to do some automation, but it's still quite limited. In addition, all these cubes, the building parts, they're limited of size. They're 1 meter, so you cannot go to a smaller pieces. And many of these models within Minecraft, they look really kind of very rough, really like in a game. And of course, it's possible with the scripting to do some analysis within Minecraft, but because of the size of the resolution of the pixels, it's a little bit difficult. So what if we get this idea? We're thinking that time about the voxels and see how we can model the real world with all kind of different resolution, and considering all kind of objects above and below the ground. And so actually to be able to do something like that from all these vector representations, to be able to provide or to create three-dimensional rasters which can represent everything from underground to above ground and even the air. And the point, of course, is how to do it, what kind of analysis we have to be able to provide on this kind of representation, and how shall we organize this information, how shall we store this information. As I said, voxels in general is not a new technique for working with real-world data. Voxels are very much used for processing of point clouds. So point clouds are usually unstructured data, usually a lot, depending, of course, on the type of the scanner and the object that is scanned. And here I have one example. So this is a tower, and it's scanned. And when it is voxelized, two things are happening. First, the point cloud is becoming structuring, because you subdivide the whole space into boxes, and somehow you introduce a structure. So you know which of the boxes are connected with each other. And the second thing is that the size of the point cloud is suddenly reduced tremendously, depending, of course, on the size of the voxel that is used. You can reduce up to 10 times the size of the point cloud, so it is easier for processing. And on the next picture, because of this structure that is introduced through the voxels, you can perform analysis for a neighborhood, and you can identify first which are the horizontally connected voxels within this tower. And after that, on the basis of some more information, you can identify which are the stairs. In the same way, from point clouds, you can identify all type of different surfaces, not only horizontal, but also inclined surfaces. And you can identify what belongs to a surface, and remove objects which are above or attached to the surface. And here is another example. So this is the original point cloud. This is the voxel space that is derived from the point cloud with a resolution of 25 centimeters. And after that, knowing what kind of objects are here, you can perform some filtering and, for example, remove this part here. I hope you see my, do you see my cursor? or do you see my cursor?
Yes.
Yes. Okay. Yeah. So this part of voxel here that is visible, this does not belong to the surface, so it can be filtered. And like this, it is possible to get all the information about surfaces. And this was just schematic representation, but here I have the real data set. This is the point cloud of one hole within one building, and the different colors represents the horizontal surfaces, the ramps with the green, and the stairs with the red. And this all is done with the help of voxels. Another very useful, let's say, application of voxel is emergency response. So when something happens in a building or in some environment, and the original model of the building is might be there, but after the let's say kind of emergency disaster, fire, flood, you see this kind of pictures within the buildings. So the original model that exists about this building is not valid anymore because everything is destroyed. And even it's not safe anymore for emergency responders to go inside such environment and to try to save people. So this is another way of using voxels for emergency response. So in this kind of environments, it's possible to send a drone, a robot, detect, collect all the information as it is in terms of point clouds. And after that, using the procedures for identification of surfaces, it's possible to specify which are horizontal surfaces in such a way to be able to walk through the horizontal surfaces and avoid all this rubble that is around. And here are some examples of another research where you can identify the surfaces, again, using voxels. Even you see here on the picture very well different cubes. And after that, provide a navigation only on the surfaces which are safe surfaces and considering the size of the human. So if you have environment, something like this with hanging, destroyed ceilings or rubble on both sides, you can select where exactly is the safe volume where a person can walk. Okay, so this was about processing of point clouds, but in a way voxels can be created from other type of data sets. Here there is I want to give you another example from creating raster or three-dimensional raster representation using existing data sets. And in this case, the existing data sets from OpenStreetMap. So the building footprints, the height of the buildings and the streets are taken from OpenStreetMap. The terrain is taken from a digital terrain model, and using specific procedures, again, it's possible to create this type of model. In here on the left-hand side, you see only the terrain with the buildings extruded, filled up with voxels according to the height of the buildings. And with this part here, you already see the streets introduced into this raster model. And this was a project that we did for New York City, specifically for emergency response and specifically for combining underground information with above ground information underground information like underground structures, metro stations, pipes and cables and other information. So underground information is usually not well represented, and here it's also possible to apply some raster approaches, starting from 2D raster and going to 3D raster in such a way to be able to create the 3D representation in a raster. And here is an example of underground station. From the underground station, only the 2D profile is taken, and after that this 2D profile is extruded along the trace of the metro station, and this model of the station in voxel space is created. And the last, probably not the last, but another approach to get voxels is to voxelize BIM models. Many of the BIM models that we have nowadays, they're within industrial foundation classes file format, and this file format can be also easily converted to 3D voxel representations. And actually this is an example of the red center of our building. You might recognize it. And the different colors represent different features within the building, the windows, the walls, the floors, the roof, all kind of ornaments around the facade of the building. And similarly, any vector model, doesn't matter whether it's an IFC format or in some other CAD format, can be rasterized. And here comes the interesting story about this different resolution of rasterization. You can have different size of voxels. For example, in this case here you see it was 50 by 50 by 50. Here is 25 by 25 by 25. And here is 10 by 10 by 10 centimeters. And having different resolution, also you have different type of models. And these different type of models can be used for different type of applications. In this case, it is really kind of very rough, still more detailed than Minecraft. You remember I mentioned Minecraft works with 1 meter by 1 meter by 1 meter resolution. Here we have already half of it, but still some information that is in the vector model, like these windmills here, they cannot be represented because they're too thin. But as soon as the resolution increases, yeah, the windmills, they also show up into the model. So that is kind of a very powerful approach for many type of applications when we model the real world, and especially when we are trying to model the space. And what I mean by space is this is the air around all these features that we have in the buildings, outside, on the streets, in the buildings. And this kind of space analysis, we need to have them for either for to estimate temperature distribution, urban heat islands, pollution. All these kind of applications are available nowadays. We can make estimations of temperature and quality of air, but somehow the information or the values related to the different analysis are linked and represented somehow to the features that are modeled with vector representations. You see everything here somehow is represented with respect to the surrounding features. Or another approach for representation is just to show, to introduce some new features like planes here, and to represent the temperature distribution on these planes, simulating that you are on the street. But of course, if we have this raster, 3D raster approach, we can model the space around the buildings, and we can really get this analysis and also visualizations much more appealing, representing the space. So here I would like to mention that I'm working with these voxels already for quite many years, and our group is very busy developing all kind of applications related to voxels. But what is very nice, now we got really a Center of Excellence funded, where we're planning to have this voxel approach really very much used. And we're going to hopefully advance all the spatial analytics that we are planning to have on the in the voxel space. This is a Center of Excellence called BRIT, and the intention is to develop technology for mitigating airborne threats to health. There are quite many faculties from UNSW involved, and a few from Monash University. The research teams are basically three: about health, aged care, and high-risk community settings, or community and other occupancy settings. And in all these subtopics we have in the teams, somehow we are going to use three-dimensional rasters. And yeah, probably next time and next year we'll be able to show some exciting 3D modeling functionality for our campus. From current research that we have, we had in different projects so far, I want to give some examples what can be done with voxels, considering the space and surroundings. The first one is visibility analysis. Visibility analysis are about estimating what is happening in the air, usually, and this can be related to surveillance cameras, what surveillance cameras see in specific area, or what can be visible from a specific walking path. In this case, different colors represent what kind of information can be visible from a specific point. I have a video on this and I'll show to you a little bit later. And here, what is visualized, these are two buildings, and this is a person that is starting walking from here to here. And everything that is shown within this blue voxels is what is visible from when the person is walking along this line. So all these spaces are well visible, and actually this is everything what is at this side of the buildings. If the people don't want to have their interior visible, probably is good to plant some kind of protection shields or some trees and some other ornaments on the facades of the buildings, so people walking along the buildings cannot see what is happening inside the apartments of the people, and in this way to keep a little bit privacy. So this is one way where analysis, voxel analysis help quite a lot. Another application is to compute volume for all kind of purposes, but specifically for taxation purposes. We have a commercial application running on this. The whole procedure is completely automatic. From large-scale topographic map and LiDAR points, it is possible to create this type of models. And of course, approximate height of the floors within buildings. It's possible to create these models. And after that, within the voxel space, for each model, very accurately can be computed what is the volume and what is the taxable area. And here what you see with different colors, with that color is the taxable area of the buildings, and here this is the brownish color is the taxable area with this building, and this area here and the greenish area here is not considered for the tax because it is less than 1.50 meters. So this application can really learn on a whole city territory, and it's a much more efficient than the current approach, which is walking and figuring out with the people what is structure of their house and whether they change something through the years. Another approach that voxels are very good is computing paths, and computing paths not only on surfaces but actually flying above certain objects or going below certain structures. So what you see here, this is a building, a voxelized building, with the red, the construction elements of the building are represented. So the walls, the ceiling, the roof. Everything else is the air voxels. And it is possible to compute in path in such a way that you say, could say, fly, for example, a drone 50 centimeters under the ceiling, or fly a drone 10 centimeters above a furniture. And this kind of applications probably not that convenient for this kind of very small building, but for very big areas where they trade with flowers, for example, or other type of goods, and you have to quickly identify how much from the it has been sold through the day. These are the same images, but then only the floor is represented here of the building. So again, something where voxels are very convenient. Here is the same in the direction of computing paths related to structuring the information in such a way that you even can get quicker the response than normally. In this case, what is happening, there is a different type of voxels in this free space. This is the airspace. This gray voxels, this is the outline of a building, and everything that is air is voxelized in such a way that only when you are very close to the walls you get high resolution, and when you are inside and there's not that many obstacles, you get higher resolution, larger cells, and you in this way actually reduce the number of voxels, and you can perform all the operations even quicker. And this way of representation is called octree. It's also well-known data structure, and a lot of operations can be run on this kind of data structure. The same when you have everything voxelized, it's very easy to compute paths for evacuation. On a voxel space, you can do all kind of operations which allow you to estimate what is the path from every point in a given floor or a building, and to pre-compute what is the time that you need to get from a specific point to the exit. And here in this case, the red ones means that they're far away, and then the green points means, the green color means that you are closer to the exit. And on the basis of this information, again, all kind of preparations can be done. Similar topic is also evacuation, when you have additional information about how certain aerosol or dangerous substance is spreading within the building. So you can follow the dispersion and you can estimate which people or how many people are in a certain area of the building, and you can take a decision how to evacuate it. This is from a project that our group is working at the moment, and what you see here is the same red center building with voxelized, and each room has different space indicated with different color. And after that, there is simulation. These are all people that you see here. And these people are also grouped according to where exactly they're in the building, which space. And having this information and having information about the dispersion, it's very easy to go to decide on evacuation. So when we are talking about is it possible to have voxels for to model urban environments, of course. There are so many opportunities about it, and these are specifically related to a large set of spatial analysis that can be done within voxel space. And these are explicitly 3D analysis, and I have here quite a list with very generic analysis that support three-dimensional analytics. But of course, there is also quite some challenges. Probably you immediately can understand when the voxels are getting very high resolution, so they become very small, like 10 or 5 centimeters, then the number of voxels in a voxel space is getting quite large, which means that you have to think how to organize all this information somewhere to be able to analyze it. The other interesting issue is in the vector domain, we are working with points, lines, surfaces, volumes. So how these point line surfaces are converted to voxels? How can we keep that lines are always connected and surfaces are always surfaces, and they don't get some kind of overlap or mixed features? For example, here I have a very good example. This is a voxelization of a building in 3 different spaces are created. Indoor space, which is with red voxels, walls with blue, and roof with green. But because of the different resolution, or because probably the wall in this part was relatively smaller than the size of the voxel, so here there is something that we don't want to have. Actually, part of the wall is eaten by the interior. So this part here, we don't have wall. So this is a challenge within voxel domain, how to keep the things valid. Of course, this relates also to the topic of the semantics. If we have this kind of situation that some object is very small, what do you do with it? Do we keep mixed voxels? For example, here we can say, okay, our object WoW is very small and very thin, so we have to integrate with the interior, but we still can keep these voxels like both interior and WoW voxels. And this kind of issues, and of course, it's also very interesting whether we need really to store the voxels or we need to go to creating them only for the time when we need to have voxels, and after that perform the analysis, and after that go back to a vector domain. So I see that I'm a little bit late, so I would like to show the video to you, and after that we can have questions. So let me start the video because it has some information about everything, and when you see the video it's actually a little bit more appealing. We're starting with this Minecraft a kind of modeling. This was a project we had back in Delft, and it's about modeling the old Delft, and especially the explosion of the gun powerhouse some time ago. And after that, we're coming to modeling our projects that we had here within University of New South Wales. This is a voxel model of the campus, and it is created from point clouds. And the interesting thing about it is that is colored according to the color from the point clouds. This is not an easy issue, and in a way we are quite happy that we managed to provide color which is quite similar to the real environment. So what you see here, it's something very interesting. These lines of people, these are actually not lines of people, these are people that are moving through the environment, and because the scanner is recording information, it recorded also the moving people several times. This can be filtered, there are approaches for this, and only the point cloud of the environment can be left out. So this is another project that we had with Lancome and some colleagues also from the university. Sorry, I'll put it here. What was this project about is to estimate what is the visibility at front of certain of a stadium, and estimate whether the protections that are at front of the stadium, like some kind of statues or bullets or trees, can protect the area sufficiently against some kind of malfunctioning ideas to drive through the crowd and kill somebody. So what is represented here is which parts of the space in front of the stadium are most visible. So these that were marked with red, they're most visible. So the assumption is that if they're most visible, so they may be most vulnerable. And here how urban planning can help with this. For example, increase the trees and increase the bollards or any other kind of protection of this area. And then if the same analysis is done again, it's visible that these red areas, red spaces, are much less. Everything that is yellow is actually quite less visible, so the driver cannot appreciate immediately what to do, and therefore it's safe. This is another project that we have with Fire and Rescue New South Wales, walking through point clouds. As I mentioned, point clouds are unstructured data, so you cannot do anything with it. And here exactly is comes the help of the voxels. We can voxelize the point clouds, create the structure, and compute a path. And after that, we can navigate safely via and rescue units through the area, avoiding all kind of obstacles and dangerous items. And the visualization still can be done in the point cloud. And actually, this is, as you see, is very appealing because the human eye recognize very well what is represented with the point clouds. And actually, the voxels help at the background to perform the analysis. And the last point is about storing all this information. We have quite a lot of experiments already by now, how to store voxels in traditional object relational database management system like PostGIS. So as you see, all these voxels are fetched from the database as we move through the scene. And this is again a few buildings from around the red center and the red center itself with all the features, stairs, walls, doors that are inside the building. And slowly like this, you can climb the stairs and you can get to any floor you want. But what is not visualized here is actually the air voxels. They're also there. And in a way, when you have the air voxels, you can perform all these analysis for temperature, distribution, for air quality, and so forth. So I'm going to stop here, and I'm open for questions. I want to thank you again for listening to me. I hope I convinced you that voxels are something very interesting, and I'm looking forward to working with you to find some interesting applications that we can use voxels. So, Chris, back to you.
Thanks, Sisi. Thanks for an excellent presentation. I'm sure there's lots of questions. I might start with one and hand over to Bala to field other questions. Just quite interested in that voxel application for looking at taxable area. Wondering if you could talk a little bit more about that. What's the data input for that, and yeah, is that what's the context of that project?
Yeah, the context was exactly to automatically estimate what is taxable area in a city, in every building in a city. So this has been done from Netherlands, and every 2 years should be again check whether the owners didn't build additional structures to the main building, and having additional structures, either additional floor, additional shed, it changes the taxable area. So this is done, actually was done manually. So there is a person that walks all the houses and checks what is happening with the places, and he checks on the really kind of manually visually what is happening. So the approach was to make this procedure all automatic. The input data are topographic maps, so the footprints of the buildings, and the LiDAR data, point clouds from aerial LiDAR. And there is a process that creates automatically the houses. And on the basis of information of first what is the year the house has been built, because according to the year, you know, approximate height of the ceilings, and the number of floors within the building. All these floors are created internally automatically. So the whole procedure is automatic of creating these 3D shapes. And when you have the whole voxel space, everything else is very easy to compute, because these are just voxels and you can basically count. Simply set the voxels within the house, and you can also count how is the height on the roof, and on the basis of the height you can decide what is the taxable area and the volume.
Very nice. And is it being adopted, or is it more of
yes, it is being adopted, and it's quite quick procedure. So
I'll be interested to find out more. Maybe we can take that offline.
we can demonstrate this to you, Chris. Yeah.
Thanks, Sisi.
It might be interesting for you. Yeah, indeed.
Yeah. Right. Conscious of time, we've got 7 minutes. I'll hand over Bala to field more questions. I also, Sisi and anyone else who would like to join us, we do have our City Futures drinks online, of course, at 5 o'clock. So maybe if the questions are still going, because we've only got 7 minutes left, we could go into another meeting room and continue over a virtual / real drink. But thanks a lot, Sisi. I'll hand over to Bala, who is our seminar series coordinator, to field more questions.
Sure. Thanks very much, Sisi. I would like open the floor for more questions online on chat. You can either ask directly or in the chat. I'll read out the questions from the chat. So one thing which I had in my mind while I was watching the presentation, how, in terms of efficiency of voxels, the voxel-based approach, how does it how does it compare to in any other approaches, as in how fast it is, or how efficient it is?
Yeah, but this is a little bit tricky question, because it depends on the resolution of and also the area that you want to process. So it's very quick if you can put everything in the memory of the computer and you can perform the analysis. So you have to somehow balance. If you want to do something on the whole city, probably you have to go to a higher voxel size. And of course, probably for the whole city, you don't need to have 5 centimeter resolution. For example, if you want to make estimates about temperature distribution, or about pollution, or whatever. The other issue is that it's very efficient in terms of 3D analysis. So if you want to compute a volume of a very complicated vector object, you know that it's quite time consuming. You have to subdivide, you have to compute to smaller shapes to be able. With the voxels, this is extremely quick. And all these operations that are based on neighborhood operations, because voxels are actually, you know where is each voxel in the voxel space, they're very quick.
Yeah.
So that's the benefit of the voxel approach. When you go to visualization, it's a little bit tricky. It's not that shiny as vector representation. And therefore, this hybrid approach probably is going to be very powerful. You have something as a vector, very nicely and very realistically modeled. And after that, for some 3D analysis, you convert to voxel space, do the analysis, and visualize it into the vector space. Yeah.
Any other questions? Yeah, and if until somebody comes up with that, I can continue the. Kishwa has a question. Thanks, Sisi. Very interesting presentation. Just curious about the cost for this 3D scanning. Is it expensive?
The CT scanning.
The 3D scanning. Yes.
3D scanning. 3D scanning is not expensive. It's getting cheaper and cheaper. And specifically within the campus, we have quite a lot of scanners by now. There are scanners in the engineering, different size, and even on drones. We also have scanners here at the at our faculty. And several colleagues have already scanned. So it's not expensive, I would say. If you want to, even there is a website where you can download point cloud data for whole Australia. It's not that high resolution. It's, I think it's 8 points per square meter or something like that. So if you want to have high resolution, you might need to either scan by yourself, hire a scanner from somewhere, or ask a company to do the scanning for you. But it's getting cheaper and cheaper. This is what I would say. The scanners are all getting cheaper and cheaper, kind of, and smaller, more and more portable. So scanning is even driven by autonomous driving. They use the scanners even to integrate them in the car for the cars to estimate how far are and where they are in the environment, and to adjust the speed within according to the distance.
Okay. Thanks, Sisi. Yeah.
Yeah, we might have like time for one more question. Anybody has one? In the meanwhile, like, so I was also interested in the last part of the presentation, which was the post storage and processing in. Okay, so we have one. So Christopher Robinson asks, has there been any efforts to use voxels for modeling dispersion of biological agent vectors with pandemic, related to the pandemic and all?
Yes, actually, there have been a lot of interesting studies. Even there is a group within engineering that they're working already for years with medicine. As I know, they have used only two-dimensional raster at the moment, but I think now they also start working and looking into 3D. And actually, this project, this Center of Excellence that I mentioned, is going to focus more and more on this approach. And if you send me a mail, I can. There was a group from Victoria that they are also working very much with voxels on different kind of applications, but they have also something for biology.
Okay. Cool.
I
Yeah,
hope
I think
it
like
was not that technical for you.
It was really interesting. Like the presentation visually was very captivating. Yeah, thank you very much for that. And I think we're coming to the conclusion. And thanks everyone for being here, and thanks very much for Professor Sisi for being here for our seminar series. And the next one would be in the next 2 weeks, and we should be sending an email via the MailChimp soon. And thank you all, and thank you very much.
Thank you. Have a good weekend, everybody.
You guys, you too.
Bye-bye.
Bye.